One was number 38.
Oh, yeah.
Wait, isn't this one?
Number 38 was the methane plus oxygen yields CO2 plus water.
You can't just do that. Make a joke and then put so.
In this particular one, I had
Lots of
Seriously.
how many? I can't remember. It was 5 liters of methane,
10 liters of air.
10 liters of air.
Right?
Yeah.
That's 298 alcohol.
Okay. And the question was how many liters of CO2? Right. All right. So 10 liters of air, we first have to figure out what the limiting reagent is. So is the limiting reagent methane or oxygen?
oxygen.
Well, it looks like it's stoichiometric because it looks like I need twice as much oxygen as methane, but this is not pure oxygen. Air consists of how much oxygen?
20%.
20% oxygen. And so the first thing we do is we do this. We do the 20 out of 100. Now, a percent or a fraction, this would be a mole fraction. You know, air is 20% by molecular mole. A mole fraction is going to be in the same ratio as a pressure fraction, which is in the same ratio as a volume fraction. And so we could just do a volume fraction here. 20 liters of oxygen per 100 liters of air. That would be our 20%. It's not the same as a mass fraction, though. The mass fraction would be different. But the mole fraction, the volume fraction, and the pressure fraction would be the same. And so this is going to give us how many liters of oxygen?
2.
Now which one is the limiting reagent? Oxygen. And then how much CO2 will we form? We can just use Avogadro's. So the correct answer should have been 1 liter. That's what it should have been. Okay, was there another one? I think.
Number 42 or 41, the one with the iron ore.
Oh yeah, that one. That's another big one. This one, the concentration of the potassium dichromate solution. I had written it as 0.5. I have the can here. Look, 0.5029 molar. Which would give you, if you use this one, then you would have calculated a percent by mass iron of 520%, something like that, correct? This is actually incorrect. It wasn't supposed to be 0.5029, it was supposed to be 0.05029 molar. And so what I did with this problem is, as long as you calculated the correct number of moles or grams of iron, then I gave you full credit for this. Because this is an impossible number. And so that's what you'll see. I just graded it up to grams of iron. And this would give us a 52.0%. All right, were there any other ones?
How much was that one out of 41?
41 was out of 8 points. This is out of 8 points, but the first, I broke it up. The first 3 points were for balancing the skeleton redox. You had to balance it because it was iron 2 plus the dichromate yields iron 3 plus the chromium 3, something like that, right? And so the first step is you had to balance this. A lot of people just use this 1-to-1 mole ratio, but it wasn't balanced. And so if you use a 1-to-1 mole ratio, then I give you partial credit for this. But if you did a 1-to-1 here and just didn't balance it, then that was 3 points right there. If you got it partially correct, then you got some partial credit for that. But it turns out we had 6 irons for every dichromate. This is the ratio, the correct mole ratio. There's a lot of confusion with, I saw a lot of people doing iron 2 and iron 3, so they're converting it to iron 3 and then converting it to iron 2. But it's a little bit weird because iron 2 is not what's in the ore. What's in the ore typically is iron metal, let's say. Sometimes iron ore could be like iron 2, sometimes the iron ore could be iron 3. And so sometimes what we do is we do something like this, where, okay, what we're going to do is we go from milliliters of potassium dichromate solution to liters of potassium dichromate, and then from liters to moles, since we have the molarity here, and then moles of potassium dichromate to moles of iron 2 plus. Reactant here. And then from moles of iron 2 plus, we go to moles of solid iron. You know, assuming that it's solid iron inside the ore, but we don't necessarily know that. And then from moles of solid iron to grams of iron. Yeah. And so this is moles of the potassium dichromate or dichromate. Since we get the net, we can just say moles of dichromate. It's just going to be the same. Okay, were there any other issues on that test? Sometimes this happens for me. And so if you see something that you don't see the answer, and sometimes I'll ask students just to write in the answer on the Scantron sheet. So take a look at those. Or write it on the test itself. You know, if you're sure, you go through the calculation and you're pretty sure that there's something wrong with it, you can write the answer in. It's not 100, because it's not out of that. Okay. All right. Any comments, questions? No. Okay, so what I want to do today is I just want to finish up chapter 7 here. The first part of chapter 7 is kind of weird with all this heat stuff. And so basically it boils down to this. You know, when we do work under constant pressure conditions, and like most of our reactions, what would you say? I'd say like 99% of the reactions, or maybe even 100% of the reactions, are going to be done at constant pressure. I mean, very few people work with bombs. And since like nearly all reactions occur under constant pressure conditions, in lab and nature occur under constant pressure. So we're most interested in how much heat are we going to get from constant pressure. So the amount of heat that we're going to get depends on how much work was done. So when we look at it, heat is not a state function. Do you recall the difference between state function and path-dependent functions?
Yeah. A state function is constant, something that doesn't change.
Yeah.
Path function depends on what happens around it.
Yeah. And so we know delta U is a state function. There's going to be a fixed amount of energy here in this change, and that's going to equal Q plus W. And so it depends on how much work is done. That's how much heat you're going to get. Sometimes we want to maximize the amount of work. But when we do things under conditions of constant pressure, then we have to compensate for the work of volume changes. In order to maintain constant pressure, the volume has to be able to increase or decrease, you know, if we form gases or consume gases. And so volume changes equals work. And we can't avoid this. This is well, we can avoid it. We can avoid it by putting it into a bomb. But if we put it into a bomb, then the pressures are going to change. So we have different scenarios. We'll take a look at the first scenario. Here's our U initial, here's our U final. So our first scenario is the work of the system. Now, if the system does work, is it negative or is it positive?
If the system doesn't work.
If the system does work, it's positive. That is, it's greater than
System's
zero.
doing the work, right?
System's doing the work.
Okay, then
So does it gain energy or does it lose energy?
because it's losing energy.
Lose energy.
So if the system, these we're going to look at are going to be exothermic right now. So the work of the system is less than zero. That means the system is going to lose energy during doing the work. And so let's look at our delta U. Our delta U is fixed. So this is our delta U. Our delta U is equal to Q plus W. Are we going to get more heat or less heat because of this work? If the system does work,
More heat. Because heat's going to be going into the surroundings.
it turns out that we get, depending on how much work is done, we get less heat. Yeah, so let's say this is the amount of heat because this is the amount of work that we just did. And so we're going to lose this much energy in the form of heat, and we're going to lose this much energy in the form of work. And so it depends on how much work we do. The more work we do, the less heat, right? The less work we do, the more heat. So that's it. All right, now, what if the work of the system is greater than zero? If the work of the system is greater than zero, then who did the work? The surroundings did the work. Now, in this case, are we going to get more heat or less heat? More heat. In this case, we're going to get more heat. Exactly. So delta U would say this is the amount of energy, but we're going to get extra energy. The extra energy is not going to come from the system. The system might be like a combustion reaction, like combusting methane. The actual energy comes outside of the system. The actual energy comes from the surroundings. So, you know, this is the amount of energy, total energy involved in this change, but we aren't factoring in our surroundings. So we actually end up getting more heat here. And the reason we get more heat is because of the work done by the surroundings on the system. So the work would look like this. So we end up with more heat than the last scenario is when the work is zero. How can the work be zero?
No changes in volume.
Yeah, if there's no change in volume, then the work is zero. And so we can see here, delta V of the system must be increasing. And so delta V of the system is greater than zero. Over here, delta V of the system must be decreasing. It's less than zero. Here, over here, delta V of the system is equal to zero or about equal to zero. Let's see. And then if the volume doesn't change, then there's no work done. So work will be zero. And so if there's no work, then all this internal energy change here will be converted into heat. Now, you can use this heat to do work, actually. This doesn't have to go in heat. It doesn't have to be as heat. You know, heat, what we could do here is this, what I like to call this is, I like to call this available energy here. And so delta U is equal to Q plus W. And then if we do some restrictions here, that is, we do constant pressure. And pressure volume work only. Then we end up with this. Q is equal to delta U minus W. Actually, I'll put these restrictions in the next step here. But the way I like to think about this is, I like to think about this as your net pay. You know, let's say you're working at a job, and you get paid, you get paid $15 an hour. But are you going to get all 15 of those dollars per hour? No, because you got to pay, taxes, right? And so your gross pay might be $15 an hour, let's say, but they have to remove the tax. That's scenario one here. In scenario one, they remove the tax, so your take-home energy is less than what you should have gotten here. So that's scenario one. There's a little tax, but sometimes somebody else pays the tax, and not only that, gives you a bonus. And so the work term could actually be a bonus. So you actually get more. Let's say you're expecting $15 an hour, but you get paid actually more than that because you get a little bonus. Here, this would be a little bonus here. And so you're supposed to get 15, but you get a little bit more. So that bonus. And then we can use that energy to do things. Or it's zero. That is, there's no tax, no bonus. You're getting paid. You get paid. Now, we don't have to leave this, we could do other types of work. The work I have here is just P delta V work, right? And so we end up with delta U is equal to, let me just write it over here. Delta U minus the work. Well, if it's P delta V work, then that's minus P delta V. And so our book has this equation. I'd like to leave it like this. It's delta U minus the work, and the work is this. Our book converts it to delta U plus P delta V. And so this is delta U minus the work here. But in this particular scenario, we restrict the work just to PV work. We could do other types of work. So what we could do is we could change this change in potential energy into not just heat, but we can take that and instead of redeeming it for heat, we can take that energy and do work with it. And so what that means is if we decide to do other types of work, we can just take this. We can't use this. This is out of our control. This is the government taking it. Let's say, the state or whatever, for your tax. And so we can't do anything with this, but we can take this and then do work with it, or we could do heat or whatever we want. And so what I call this the usable energy here. Your net pay is your usable pay. You can actually do something with it. Your gross pay, you can't typically do anything with it because you don't have all the dollars. But this would be the usable energy here. And it doesn't have to be heat. It could be work, because we could take that and do more work and have less heat here. Or it could be heat. It depends on how we redeem it. So there are different ways we could redeem this. When I say usable energy, we can convert it all to heat. That is, Q can be converted all into heat. If it's all converted into heat, then if we wanted to do work with that, we'd have to use a heat engine. Heat engines are notoriously inefficient. A heat engine, can you think of an example of a heat engine? Something that just takes heat and
Creates energy.
creates work.
Geothermal.
Geothermal is...
It's a lot more efficient. It uses water and power.
Yeah, well, geothermal is pretty efficient, but heating it, because it's really efficient because you don't have to pay anybody to heat it.
No.
But if you have, let's say, I'm going to build my own geothermal plant inside the house. Would that be very efficient?
No.
It wouldn't be, because you'd be sitting there boiling the water, and that's going to cost you a lot of energy. And so it's a terribly inefficient way of doing that. So if we use all this usable energy, and convert it all into heat and then try to convert it into work, it's not very efficient. It would be like a steam engine. That's what geothermal would be, a steam engine.
Well, it's terribly inefficient in creating work out of it.
Right, but what we're doing here is what we're going to do is we're converting the chemical potential energy into heat and work. Then this is much more efficient. You know, we can get much greater efficiencies here. And so, you know, some people who have had physics, when they think about heat, they think about something called the Carnot cycle and heat engine efficiencies and this kind of stuff. Well, this is a little bit different because we're taking a step back, and this is actually chemical potential energy. The chemical potential energy can be converted into heat and or work with good efficiency. And so this is inefficient. However, this is what we can do here. This would be efficient. So it doesn't have to all stay as heat. And so this is what I'm going to call usable energy. When we do this restriction here, this is not a state function. So up to this point is not a state function because we can do any kind of work, and depends on how much work we get. That's how much the chemical potential energy, remaining chemical potential energy, can be converted into heat over here. Whereas over here, this is what we call Q sub P with PV work only. And if we look over here and just do this part, actually, I should define it over here. We call this delta H. So delta H is the usable energy. It's whatever internal energy, whatever chemical potential energy is left to change. It doesn't have to be chemical. It could be kinetic if we're looking at objects too. But if we're looking at objects, it's just going to be heat. It's not going to be chemical potential energy. In this case, if this is a chemical potential energy change, if this is just a heat change, then we're stuck with inefficient. Like hot object, can you power your car with a hot block of iron? No, it's not going to be very. You can warm it up. Right. You can warm it up for sure. All right, so this delta H is the usable energy. It's a usable potential, well, we'll just say usable internal energy change after we factor in the work. Now, the work can be tax, bonus, or zero, but we can't control that. That's out of our control because we're doing it under constant pressure. And so this is delta H is usable. And so if that's the case, and we do nearly all our reactions under conditions of constant pressure, then we don't really care much about U. The only reason we need to know U is because we do bomb calorimetry. It's just easier to do it in a bomb than under constant pressure conditions. It's safer to do certain reactions in a bomb. And so, this was exothermic. I should do the endothermic scenario here. This is going to cost us energy. So delta U is positive. It's an endothermic. It's going to cost us energy. How much energy is it going to cost? Well, we have to factor in the work because that's out of our control. How much tax are we going to get? Are we going to get a lot of tax for this? Or what? Let's say we're going to suffer from high taxes here. So the work of the system is less than zero. Well, that means how much energy am I going to have to input, either in the form of heat or in the form of potential, chemical potential energy or whatever. Well, delta U is equal to Q plus W. And so what that means is I'm going to have to input more energy than I would expect because I have to do, in addition to this chemical potential energy change here, I'm thinking about reactions mainly here, although I could also be thinking about objects. So, it's a good thing to try to get things sorted out in your mind. But this is going to be Q and this is going to be W. Because this is an additional tax, I have to input more than I expect. So this is like, when you go to buy a television or something like that, or a computer, you're going to have to pay more than the price, the list price on that. So that's not a big deal, but this tax is unavoidable. And so we don't really care about what the list price is. We care about what the out the door price is, the price with the tax. And so this is going to be more useful for us. Sometimes somebody else pays the tax. If somebody else pays the tax, then they have those Memorial Day sales or whatever. And so here, the amount you pay is going to be less because somebody else had to do that. And so this is the work in the system was actually done by the surroundings. So we end up paying less. And then finally, there is one of those tax, I forgot what day this are, but it's one of those tax-free sale days. I mean, they still pay the tax, but somebody else pays the tax. Here, this would be tax-free. You go to the, what they call it, the international airport.
You go to the department store, right? And they're not supposed to sell food, but they sell food, but they can't sell with tax.
Right, so we have that, where the work is zero. So this is an endothermic variety. But ultimately, we're not going to really worry too much about this. Ultimately, we just care about, what Q is. Now, if we do the QP, this is the constant pressure. Whenever we use delta H has to be under conditions of constant pressure and pressure volume work only. And so if we're under constant pressure and PV work, then delta H is what we care about. We care about how much is it going to cost me. I don't want to know what the retail price is. I want to know what the price is, including tax, or if there's a sale or whatever. And so we really care about that. And so instead of having an internal energy diagram, we're going to have what's called an enthalpy diagram. The enthalpy diagram will just look like this. Well, this will be exothermic, let's say. And so we'll have an initial enthalpy and a final enthalpy. And we'll have a delta H here, the change in enthalpy. Our delta H is, the QP with the restrictions. And our delta H is going to actually equal delta U minus W. And since the type of work we're doing is minus P delta V work, this comes out to delta U plus P delta V. And so when I look at this, H initial is just equal to U initial plus P. P's constant, V initial. H final is equal to U final plus P V final. So basically, enthalpy is the same thing as internal energy, except we have to keep track of volume changes and pressure so that we can figure out how much work is done by the system or how much work is done by the surroundings. That's in other words, if you recall, pressure volume is energy. Liters will be volume, atmospheres will be pressure. So liters atmosphere is energy. And so enthalpy is just the internal energy, that is the total energy, plus the PV energy.
What does it say after delta H equals?
QP. This is supposed to be Q sub P. Usually when we say delta H is intensive. Delta H is kilojoules per mole. However, when we say QP, that's intensive. Maybe I didn't burn a full mole. Maybe I burned a tenth of a mole. So I'm going to get a lot less heat. So, sometimes they aren't exactly equal. So what we do here is, this is the definition from thermodynamics. In practice, it's like this. Q sub P depends on how much you burn. So it's the amount times delta H. Delta H is kilojoules per mole. So if we burn a mole, then that we get that many kilojoules. Or delta H is equal to QT, how much heat for how much amount, you know, kilojoules per half a mole or kilojoules per tenth of a mole, and then we can just divide it and get it kilojoules per mole or gram, whatever you want. Intensive. Delta H is typically intensive, but Q is typically extensive. And so they're the same thing, it's just, you know, how you want to express it. You want to express it for a certain fixed quantity, or do you want to express it for some per, you know, per mole or per gram quantity? That's essentially the same thing. It's this. How we play this. So I'll put a little footnote there. So when we're dealing with delta H, I don't want to think, you know, was it a tax? Was it a bonus? Was it zero? You know, you don't have to think about it. We just use delta H, and that's the usable energy. Now, once we have that usable energy, it doesn't have to be all in the form of heat. I know Q is the symbol for heat, but we could convert this, put internal energy change into work as well. So we could use this energy to do work. But it's not like first it has to convert into heat, and then it has to convert into work. We can just convert it directly into work. Unless this is an object. If this is a hot chunk of iron going to a cool chunk of iron, then it's just heat. You know? And then we'd have to work on converting that to work, which isn't terribly efficient. So this is our endothermic case here. Or not exothermic. No, endothermic would be wrong. So. Now this is the net. And so it depends on who did the work. You know. And so if we're looking at delta TU, and so we don't want to mess things up too much. But if we're looking at delta U, you might think, okay, this is what I'm paying out the door, but what was the retail price of this? And so it depends on who did the work. So for example, let's say the system did the work. If the system did the work, then it's less than zero. What would delta U look like? Well, how do we do this now? Okay, delta U, and if the work is less than zero, then this is minus a minus, which gives us a plus. And so this would be something like this. You know, this would be delta U, and then the work here. Is that right?
Yes.
Yeah. If the work of the system is greater than zero, then it, delta U must have been, yeah. I guess delta U must be something like this, and the work must be something like this. This is for enthalpy, delta H. Is that right? Sometimes, you know, thermodynamics, you have all these relationships, and they're so easy to get all mixed up. But delta U is equal to delta H plus W. So we have to think, if delta H is Q. And so, anyway, this requires some thinking. I don't know if I got this right, but we'll do some problems to see, etc. Check these. Okay, if we have an endothermic reaction, it's just like this. Now, we never use this. For example, if I wanted to calculate delta H, I'd never do H final minus H initial. Why? Well, pressure volume is no problem to measure, but U is difficult. These are called the absolute. And so just like absolute internal energies, absolute enthalpies are never determined. absolute enthalpies are not determined. Well, they're not determined with any accuracy. And that's because absolute internal energies are not determined with any accuracy. So we never do this calculation here in this way. So let's see if we can figure some of these things out. The relationship between enthalpy and internal energy. All right, 63. Only one of the following quantities is equal to the heat of a chemical reaction, regardless of how the reaction is carried out. So, if we carry out the reaction under constant pressure or constant volume, it doesn't matter. We get the same amount. So, which one would it be? Or which ones would it be? So let's try this one here. This is a little bit of a trick question here. Which one and why? Well, let's first talk about QV. What does the V stand for? Constant volume. And if we do it under constant volume, QV may not equal delta H. The only time where QV equals delta H is if delta V is equal to, delta V under constant pressure is equal to 0. Yeah. But QV is always equal to delta U if the work is 0. All right? Yeah, under constant pressure. Because under constant pressure, the work is 0. At least PV work is 0. Right? I should write that, PV work. And PV work is the natural work of a chemical reaction. And they aren't saying that we're doing any other kind of work. They're just saying a reaction is carried out. And so we know that delta U is equal to Q plus W. Well, under constant pressure, wait, no, that's wrong. Not under constant pressure. This needs to be corrected. It's under constant volume that no work can be done because the volume can't change for chemical reactions. And we're not doing any electrical work or anything else. So the W term here is just 0. And so QV is delta U. Because we can't do any work in a constant volume container. So this is kind of weird because QV means we have to do this under constant volume, and we can't do it in any other way. So what would you say about A? Is A going to be the same regardless of how the reaction is carried out?
No, because if it's not under constant pressure, it would be a different answer.
Yeah, it would get a different amount of heat. So that's acceptable there. Some people will say, no, QV is always the same. Let's say the speed limit is 55 miles an hour. But let's say you have a really fast car and you can go faster than 55 miles an hour. Is the speed limit still 55 miles an hour?
Yeah.
Yeah, it doesn't matter. And so it doesn't matter how you do the reaction, this never changes. And so the other answer for this is this never changes because if you do it under constant pressure, QV is still going to be the same number, right?
Yeah.
And so this is like the speed limit. It doesn't matter how fast or what conditions you do it under, QV never changes, right? And so in that state, QV is no longer what we call a path-dependent function. QV is a state function. Because if we do this reaction under constant volume, no work can be done. The work is screwing things up. How much work you do changes how much heat you get. And so that makes this into a state function. The state function is like a speed limit. You know, this we could do it any way we want, but this is never going to change. Does that make sense? And so this is going to be a state function. And therefore, I would say A doesn't change. If this were Q instead of QV, then I would say that would be a better answer. You know, depends on how you do it. Does that make sense?
Yes.
Yeah. So QV is a state function as long as we're dealing with constant volume and a chemical reaction.
Wait, so does QB imply that it's always going to be constant volume?
Yeah. It's like this. Okay. What is the molar mass of helium? Well, it's 4 grams per mole. But now I'm going to talk about hydrogen. And I'm going to spend all my time talking about hydrogen. Is that going to change helium's molar mass? No. But you know what? I'm not even going to use helium. If I didn't use helium, will that change helium's molar mass? No. And so this is the same kind of thing. The AA battery has this much energy content, but if I decide I'm going to go to D cell batteries instead of AA batteries, is that going to change anything with the AA battery? It doesn't, regardless of if you use it or not. And so that's the same thing here. It doesn't matter if we use this or not, it doesn't change. You know, QV is fixed. It's like the speed limit, it's fixed. We can't do anything about it. That QV is fixed. If we happen to do the reaction under these conditions, then that's the amount of energy we get. But if we decide to go a full different route, you know, we're going to do mechanical energy mechanical work, we're going to do electrical work, we're going to do all kinds of work, then that doesn't apply here. You know, this is still fixed, but it's not going to apply to our particular problem. Just like the molar mass of helium doesn't apply to any problems with hydrogen, unless you're doing fusion. And so that's why I would say that A doesn't change regardless of how the reaction is carried out. It doesn't apply, you know, it's important. If you do it under constant pressure, A doesn't apply at all, but still A doesn't change. It's still the same number. It's still the same number because it's what we call the delta U. When we do this under constant volume, the heat is a state function. We're always going to get the same amount of heat.
So is QB the energy if it were carried, like the reaction is carried out in a bomb?
In a bomb, right. In a bomb, it's QB. It doesn't have, you know, we can't do any work inside a bomb, so it's all going to be generated, converted into heat. At constant pressure, we can use the heat to do other things, like go directly to work rather than heat. Here, we're not going to go directly to work unless you put some machine inside the bomb. Now, if you put some machine inside the bomb, then yes, you could do work, and we get a little bit different amount of heat. But this is what we're saying is, for chemical reaction, the only type of work we're going to do is pressure volume work, expansion and contraction. And so this is a state function. In fact, QV is defined as delta U. But, you know, all these symbols, you know, this is the hard part of thermodynamics. The hard part of thermodynamics is keeping track. You have to know, okay, what is QV? How does it relate to QP? How does it relate to Q? You know, this is why so many people fail thermodynamics. And these are like chem majors. The chem majors failing thermodynamics is common. Thermodynamics, you got to keep track of all these things. I was very at risk of failing thermodynamics too, because when I took general chemistry, they never talked about this stuff. You know, it was much easier just to talk about delta H rather than all this stuff. And so I had to go back and learn all this to catch up. I had a lot of catch up to do. So I just barely made it out of that nosedive. And so this is a really good book because a lot of books ignore this completely. You know, because it's too confusing. sometimes. What about QP?
Um,
Uh-huh.
yes. I believe that we would have a very similar problem as with QV, as in under constant pressure, it would be equal to the heat, but under constant volume, it would not be. As QP allows for work to be done while QV doesn't, which means that QP is constant in constant pressure, but not in constant volume, meaning that it's only partially correct.
Okay, that sounds good. Yeah, QP doesn't change. You know, QP doesn't change. In fact, QP is what we call delta H. So delta U and delta H don't change. Those are fixed. Enthalpy. QP is enthalpy with PV work only. If you throw in other types of work, then it no longer works out. You know, it's constant pressure plus PV work only, but they only put Q sub P. But we should probably put Q sub P slash PV, you know, to indicate that it's restricted. And then it's always the same. So this is like the, you know, what's the speed limit in Canada? Well, I'm never going to go to Canada, but does the speed limit change? Or is it fixed? Well, it's fixed for at this time. So anyway, so I would say A doesn't change, B doesn't change because they might not apply. It's not saying which of these apply.
But which of these is correct?
Yeah.
In any way.
Right. How about this one? C, delta U minus W. Oh, that sounds familiar. What is delta U minus W?
Delta U minus W. That's Q. That's
That's QP, aka
Delta H.
delta H. Delta H is a state function. It doesn't matter how you do it, right? It's always the same. And so delta H doesn't change. Well, the thing is, does delta H apply if we do this under constant volume?
No.
No, it doesn't apply. So if you try to use this under constant volume conditions, then forget it. It's not going to work, right? But where does it say we're restricting it to constant volume? And where does it say we're restricting it to P delta V work only?
We're not.
We're not. And therefore, is this always the same?
No.
No. This is not always the same because we didn't put this restriction on here, did we? Had we put those restrictions on, yes, then it might not apply, but it will always be the same because it's a state function delta H. Do you see how thermodynamics is kind of confusing?
Yes.
And it takes time to work this out?
Are you saying for C that since it isn't defined as constant volume or pressure, that it becomes a
Yeah, it depends on how much work we do. There's no restriction in the work, so we could do lots of work or a little bit of work.
it becomes a path function.
Right, but so the amount of this is going to change depending on what conditions you do it. If you do it in a bomb, there's no work, so we're going to get more energy. If you're powering a machine, we're going to get, we're doing lots of work and we're going to get less energy as heat.
Does that mean the context of this question is a path function? Because depending on whether or not we put it into a bomb or not,
Yeah.
changes the value that we will get out.
Right. So these ones restrict things here.
Because
Although this one, there's got to be one more restriction here. The one more restriction, and actually there's two more restrictions for this. We can't put a little machine into the bomb that does work. And over here, we only have to do the natural work of a chemical reaction, that is expansion and contraction.
I don't think they expect us to do that.
I don't know. I should take a look at the answer. This is number 63. So we'll check the answer. I can
Pull out the answer.
Okay. How about a D, delta U? Well, delta U is always the same. That's like your AA battery. The AA battery always has a fixed amount of energy. What you do with that energy can change. So the amount of heat you get and the amount of work you get changes depending on what you're powering with your battery. If you're powering a little fan, you're going to get a lot more work. If you have a little heater, it's going to generate more heat, but the total amount of energy is the same. So delta U is going to be fixed. Okay, we'll check it. We'll check our answers in just a second. How about E, delta H of a reaction? R means reaction.
Same problem as delta U.
Well, delta
similar,
U,
similar problem to delta U.
actually, delta U doesn't matter if we do this under constant pressure or constant volume, it's going to be the same. The amount of heat you get is different. But delta H is restricted. Delta H can only be done under constant pressure. And so it depends if is it a trick question? You know, because delta H restricts it under constant pressure, so we already can't do all the reactions, but delta H doesn't change in itself. Delta H is always the same. So when I burn a mole of methane, I'm always going to get the same amount of heat under constant pressure conditions. So I would say that delta U and delta H don't change. These are fixed. So the only one that can change is C, depending on how much work we do and the conditions we do it under. So what was the answer?
So the answer was C,
Oh, okay.
right? And the explanation given by the book is that both A and B are heats of chemical reactions carried out under conditions of constant volume and constant pressure, respectively. And both delta U and delta H incorporate terms related to work as well as heat. So,
All right, that's not a very detailed
it's
answer,
not. So
but that's okay.
the way I interpreted it was that A and B are defined under premises, meaning that they can't change unless they are pulled out of that. And the same applies to D and E, as delta U can only be applied in a certain scenario, and delta H can only be applied in a certain scenario.
Delta U can be applied in all scenarios. Delta H is the one that's restricted.
Yeah.
Remember, delta U is not as convenient because since it applies in all scenarios, we don't know, is the work going to be a tax? Is it going to be a bonus, or is it going to be zero?
Yeah, that's
We
why I'm
don't
saying
know.
just delta U without work.
Yeah. Okay. Yeah. Delta U without work would be QV.
Yeah.
So,
And since we have delta U with work, that means that we can't assume work with delta U.
okay.
And with delta H, we can assume work because of its conjugate, but delta H is only QP,
Okay.
which means that D and E is basically just AB at a certain time.
Well, let's try this one. 64. Determine whether delta H is equal to, greater than, or less than delta U. So delta H is your net pay. Delta U is your gross. This is for exothermic. Or in endothermic, we have to think of cost. You know, and so let's think about this a minute. And so for the following processes, keep in mind that greater than means more positive or less. Actually, let's ignore this. Greater than or less than for right now, and just try to think in terms of energy. The complete combustion of 1 mole of butane, 1-all. So butanol has 2 different isomers. There's butane 2-all and butane 1-all. What's the difference?
The location of the alcohol.
Yeah, the location of the alcohol. And so this one will be, butane is how many carbons again? 4. And we'll throw in the alcohol on carbon 1 and just write that backwards. And so when we balance this, probably, let's go ahead and balance it here. Is it going to be exothermic or endothermic? It's going to be exothermic, so we're going to make CO2s. We got 4 carbons, so we'll make 4 CO2s. And how many hydrogens do we have? 10 hydrogens. So we'll need 5 waters. And how many O2s will we need? 13. 4 times 8. 4 times 2 is 8, plus 5 is 13. But this is 1. 1 plus how many will give us 13? 13. Okay, so this would be true. The next thing we need to know is butanol a gas, liquid, or solid?
Should be, it's an alcohol.
I would say it's a liquid, right?
Yeah, because
Yeah, it is a liquid. Water, gas, solid, or liquid? Liquid. And we're going to do this at 295, or not 295, 298 Kelvin. And that means O2 is a gas and CO2 is a gas, right? All right, so the question comes up here. We want to know is delta H versus delta U. Which one is going to be bigger? Delta H or delta U? Or actually, if we're doing delta U, we might as well start off with an internal energy level diagram, U. And delta U is going to be just this drop here. And so this is the net, or not the net, this is the gross. Okay. So that's the gross energy change. But now we got to figure out who did the work. Did the system do the work or did the surroundings do the work?
The systems did the work because it was releasing energy into the surroundings.
And that's not how we determine it. How we determine the work is by, did the system blow up the balloon or did the surroundings blow up the balloon?
The system blew up the balloon.
How did you determine that the system blew up the balloon?
Let's see. So the way we can do it is by determining volume for.
Yeah. Do I want to look up the density of butanol is pretty easy to look up, and if I have a 1 mole, I can figure out how many. But normally, gases and liquids, actually not gases. Normally, liquids and solids don't have much volume. But gases have a lot of volume because they're mostly empty space. And so oftentimes we'll just ignore the liquids and solids and just focus on the gases. Let's look at the gases here. If I have 6 moles of O2 at 290 Kelvin, and we're going to assume 1 atmosphere pressure, about how many liters is that? 150 liters. And then 4 moles of CO2 is going to be about how many liters? 100.
Yeah.
So we're going from 150 to 100. We're losing 50 liters. So that 50 liters is about, 50 times 100 joules per liter is about 5,000 joules worth of energy, about 5 kilojoules worth of energy. Who did the energy? Who lost that? That's 5 kilojoules of energy to blow up the balloon or shrink the balloon. Who did that? Who blew up the balloon in this case? If the system loses 50 liters, that means the surroundings must have gained 50 liters, and therefore the surroundings blew up the balloon. Which means what? Which means, is that a tax, bonus, or are we just even, zero?
Tax.
It's a bonus, right? Yeah, so we got about a 5 kilojoule bonus from the work. This is the work of the system's positive. The work of the surroundings must be negative. The surroundings must have lost that 5 kilojoules. So what we're going to get is we're going to get an additional 5 kilojoules worth of heat. That heat we can use to do different things. We don't have to leave it as heat. We can convert that into work directly from this. This is a chemical potential energy change. And so that means we get more energy than the internal energy. And that extra bonus of energy came from the surroundings. So what we say is this. Now, this is, let's say delta U, I don't know what it is. I could look it up, but let's say it was like, minus 2,000 kilojoules, I guess. That means delta H is minus 2,005 kilojoules. Now, it depends on the author. Which one is greater? Minus 2,000 kilojoules or minus 2,005 kilojoules?
Minus 2,000 kilojoules.
Minus 2,000 kilojoules is greater?
This is in the terms of energy. So
this is in terms of energy. And so which one is a greater energy change?
2005.
2005. But what they're saying is this. I don't like this. Keep in mind that greater than means more positive. So which one's more positive?
2000.
2000? is that really the greater energy change? No, the greater energy change is this. So that's why I don't like that. And so the correct answer for me is this, is a greater energy change. But the book is going to have this, because it's more positive. You know, does that make sense?
What is it? So, what if one's positive and one's negative? Say there's like positive 2,000 kilojoules.
Yeah, then if they're both positive, then it's good. But if they're both, one's positive, one's negative, then
It's an absolute value type thing.
yeah, okay, this. Let's say the temperature change was 10 degrees C for apparatus A and minus 1,000 degrees C for apparatus B. This is my delta T. Which one's greater? Temperature change, delta T. Negative 1,000. But if we're using this ridiculous thing called the more positive result, then this is the answer. Do you like that answer? No, I don't like that answer either.
I see it was 3 zeros, I assume that's the big.
This is why some books say take the absolute value. And the absolute value will tell us the magnitude of the change. So if we take the absolute value, then that fixes everything. And then we take the absolute value of this and this. This is why I say that there's no such thing as negative energy. But whatever.
Take the absolute value.
Okay. The complete combustion of 1 mole of glucose. So let's do the same analysis here. This is going to be exothermic as well. C6H12O6, solid, plus O2. It's going to go to, we have 6 carbons, so we'll need 6 CO2s. And we have 12 hydrogens, so we'll need how many waters? 6 waters. And we need 6 O2. 6 O2 gas. Yeah. So since we're comparing delta U and delta H, it's easier just to write the delta U rather than write the delta H and work backwards, because then it gets mixed up again. We'll do a calculation. All right. So what do we have here?
We have a mole of glucose, 6 moles of O2.
Yeah. A mole of glucose is 190 grams, roughly.
Yeah.
100, yeah, something like that. 190 grams would be about, glucose is going to have a density about twice that of water, so it's about 90 milliliters. 6 moles of water, that's 6 times 20, let's say, about 120 milliliters of water, roughly less than 120. So it's about break even. You know, glucose is a little bit more dense than 2. And so even though this is solid and only 1 mole, and this is liquid and 6 moles of that, their volumes are going to be approximately the same, within 10 milliliters or something. 10 milliliters is not going to be much work. This is 0.01 liters. What about this? Yeah, 6 moles, 6 moles. So what do we say about delta V? Delta V is going to be about 0. If delta V is about 0, then how much work are we going to do? Or
Do about
none. And therefore, if we don't do any work, then all of this will be equal. Yeah, this will be Q. And therefore, Q is delta H if we put some restrictions. So delta U and delta H are the same. The decomposition of solid ammonium nitrate to produce liquid water and gaseous dinitrogen monoxide. This one's exothermic as well. Ammonium nitrate is inherently unstable. It's solid. And in this case, it's going to decompose into liquid water, H2O liquid, and dinitrogen monoxide or nitrous oxide. gas, laughing gas. Don't try this at home to generate your own nitrous oxide at home.
That seems a little
Um,
dangerous. H4 and NO3.
Yeah,
Especially together.
yeah, especially together. This is, Oklahoma City,
Seems kind of violent.
Lebanon, Beirut. This is in China, and Texas City. Texas City was the biggest.
Seems a little explosive.
Yeah, it's explosive. So you might think I'm going to try to generate my own nitrous oxide, but this is not the way to make it.
What is the way to make
The N2O production. If it was not even if it was high enough, just because it was there.
I don't know the best way to make it. Yeah, you can play around. Anyway, what's going to happen here?
From approximately
Yeah, explosion. In an explosion, we need rapid, sudden volume expansion. Rapid, sudden volume expansion means we're going to have a shock wave, and that shock wave, it depends on how fast the shock wave is. If it's faster than the speed of sound or slower than the speed of sound.
make for one interesting bomb.
All right, so anyway, we're going from, okay, this is solid, this is a liquid, so we're just going to say it's break even, or close enough to break even. We can actually calculate it. I mean, these are easy to look up, but it's just going to require time. And so if we're doing, more precise, more accurate work, we probably calculate the volume of this and the volume of this, but essentially this is 25 liters, so we're increasing the volume by 25 liters, and who's doing the work in this case?
The system.
The system. The system's blowing up the balloon. If the system blows up the balloon, then some of the energy is going to be consumed in doing the work.
So when that create a tax.
Yeah, so delta H is going to create a tax, so we're going to get less energy than we can use to do work on this. This is doing the work of this, generating that explosion. In this case, delta H is going to be smaller than delta U. Typically, they have these questions like this. I mean, how would you answer this? If you said delta H is smaller than delta U, you would write it like this: delta H is smaller than delta U, right? But when you put numbers on this, then it screws things up, because let's say delta H is minus 800 kilojoules and delta U is minus 1,000 kilojoules. And so you have to be very careful in multiple choice, because which one is greater? Yeah, in terms of a delta, in terms of a change. '65, the heat of combustion of 2-propanol, or propane 2-ol, at 298.15. So determine, this is a bomb calorimeter. Is 33.41 kilojoules per gram. Is that a delta U or delta H? Yeah, this isn't a bomb calorimeter.
Delta V.
And so this is delta U of combustion for propane 2-ol. 2-ol is minus 33.41 kilojoules per gram. For the combustion of 1 mole of propane 2-ol, determine delta U and delta H. Well, this is delta U, but this is delta U per gram. What they want us to do is they want us to get the delta U per mole. So that's not hard. I mean, what we have to do is we have to look at how many carbons do we have. Propane 2-ol. Do you know another name for propane 2-ol?
Isopropanol.
Yeah, isopropanol or isopropyl alcohol. That's propane 2-ol. rubbing alcohol. So how many carbons? 3 carbons. It's 3 times 1201, which would be 3603. How many hydrogens? 8 hydrogens, so this is going to be 808 hydrogens. And 1 oxygen, 1600. And so this is going to give us 11 and 14, 20, 60.11. So all we do is we convert it from grams to mole. The part one was pretty easy, just a one-step dimensional analysis problem. So what are we going to get in kilojoules per mole?
No one will find my calculator.
3341 times 60.11. This is 2008. 466.2 kilojoules per mole. Yeah, it's still negative. That's okay. Okay, what is delta H though? So let's figure out what's happening with the combustion of propanol here. Yeah, and so let's first figure out is it bigger, smaller? Who's doing the work? Let's try to figure that out first. So propanol, 2 propanol is going to be CH3 with OH stuck in the middle, plus O2. This is going to yield 3 CO2s plus 6, 7, 8, 4 waters. And then this gives us 6 plus 4 is 10 oxygen. So 1 plus how many oxygens?
Wait, we need 10 oxygen.
Yeah, we need 10 oxygens.
We need 9 over 2.
Yeah, 9 over 2. Now, we do not double this. We have to leave the fraction in place. Why? I'm not going to double this because this is per mole. And so it's per mole of propanol or isopropyl alcohol. 2 moles. I don't want to do that. Because if I'm going to calculate the volume, I got to do it per mole of propanol. Does that make sense? Yeah. Now, propanol is a liquid. Oxygen is a gas. CO2 is a gas. Water is a liquid. Now, this is my delta U. So who did the work? We're going from 4.5 moles of gas to 3 moles of gas. So 4.5 moles would be what? 2,500, 112, roughly 113 to 75. So who's doing the work? The surroundings is doing the work. And so that means our delta H is going to be bigger because the surroundings will do some work to contribute there. Well, what we need to do is we need to figure out how much work that is because delta U is equal to delta H plus W. Or not plus, yeah, plus W. And so if we want to figure out what delta H is equal to delta U minus W. In other words, delta H is the net is equal to the gross minus the work. All right, in this case, how accurate do you want to calculate this? Well, we'll just try it at least once accurately. And so what I'm going to do is I'm going to go to propanol and see what the density of propanol is. Actually, I'll just do isopropyl alcohol. And let's go to Wikipedia.
Oh, density.
Okay.
786 kilograms per meter.
All right.
What's the first one?
786. You know, this is 0.786 grams per milliliter. 0.786. So the molar mass of this is 60.9 1 grams. So we have 60.1 grams of isopropyl alcohol. I'll just call it IA. And the density is 1 milliliter weighs 0.786 grams. I know they use funny units there. They use funny units. Oftentimes they use funny units because they don't want any decimal point. Decimal points take up space. And they want a lot of sig figs.
They take up characters.
Right. And then we're going to convert this to liters. And that's going to tell me the volume of the isopropyl alcohol. So let's try that, of 1 mole of isopropyl alcohol. So if I have 1 mole of isopropyl alcohol, it weighs 60.1 grams divided by 0.786 divided by 1,000.
0.07646. We are allowed 3 significant figures, so that's 0.0765.
Yeah.
7646.
Yeah, I'll just do it like this. Liter. So about 76 milliliters. All right. Now I'm going to do this a little bit more accurately because they said what did they say? 273.15? If they're being that precise with the temperature, then I probably should be a little bit more precise.
298.15.
Yeah, 298.15. And so what I'm going to do first is I'm going to calculate the molar volume. The molar volume is equal to RT over P. That is V over N. V over N is equal to RT over P. So this is 0.08206 liters atmosphere per mole Kelvin. Are we doing this at 1 bar or 1 atmosphere?
We're calculating constant pressure, so it has to be at 1 atmosphere.
It doesn't have to be at 1 atmosphere.
We should calculate at 1 atmosphere for room temperature.
Yeah. A lot of our data, we have to be careful with our data here. If you look at this chart, do you see the footnote on this chart?
Yes.
Gases are at 1 atmosphere. So what we need to do is we need to go to our appendix D. And our appendix D is going to have all our thermodynamic data here. And so I want to go to appendix D quickly and take a look. I think this is D20. It should throw me in there in the right range here. For A, I'm going to go to A20D. I'm going to go to the beginning of this table. Let's see what they use. So table D2, thermodynamic properties of substances at 298.15 Kelvin. Substances are at 1 bar pressure. Shoot. So I am going to use 1 bar so to keep it consistent. And so how do I change atmosphere to bar?
1.01325.
1.01325 bar per atmosphere. So I'm going to calculate the molar volume in bar. Although most of the time we use atmospheres, but it's close, so it's not going to be that big of a difference anyway. 298.15 Kelvin. The pressure is going to be 1 bar. And so what is the molar volume?
24.790366.
Yeah, equals 24.70 79036 liters per mole. Okay, we don't have to be that precise. Okay, so I have 9 halves. We'll just call it 24.79. We're out of time. 24.79, and I don't really want to rewrite this, but we'll have to. And I wanted to finish it, but we'll have to finish it next week then. All right, so I'll stop here. But you can see the calculation is not that difficult, I think. Right? We'll finish this calculation next time.